This section is about Green's theorem, section 15.4, and the goal here is really to continue our study of the fundamental theorems we get when we look at multivariable calculus. So just to set things up, remember that in the last section we had this following identity when f is a conservative vector field. That is, it's the gradient, it's the derivative of some potential, of some function middle. And there, we somehow recover an analog of the fundamental theorem of calculus. That is, if you integrate along a curve from point A to point B, the component of f along that curve, so that's a line integral, this is equal to the potential at the last point minus the potential at the initial point, okay? So in the end, the line integral only depends on the endpoints. And in particular, if C is a closed curve, so the first point and the last point are the same, so you get 0. And again, mathematicians like to be fancy and put a little circle to warn you that the curve is closed. All right. Now, question, what happens when f is not conservative? Well, you can always compute the line integral, right? Get the velocity vector of the curve, do the dot product with the vector field, and just integrate. But do you have some sort of identity, okay, for the right side? Maybe not 0, but maybe something else, and that's Green's theorem. Okay, so let's actually illustrate the theorem by an example first. So let's take that vector field, minus yx. I like that vector field. It's like the whirlpool, okay, where it actually rotates. That's not conservative. We did that in class. You can check the mixed derivative. All right. Now, can we compute the integral of the line integral of f along the curve C, which is the unit circle? Okay. The answer is yes, and let's do it. All right, so let's compute that. So how do you compute the line integral? Well, first of all, I have I'm going to parameterize my curve by the theta, the unit circle, so by the angle. So theta goes between 0 and 2 pi. The position on the circle is given by cosine and sine. So the vector field at the point cosine sine is minus sine, which is minus y, plus x, so cosine theta. All right? So, good. Now, what is the velocity vector? Is the derivative of the position. So position is cosine and sine. So the velocity vector is minus sine cosine. Okay. So when I do the dot product between the vector field and the velocity vector at the value theta, I get cosine sine square plus cosine square. So I get 1. So I get when I integrate d theta, I get 2 pi. Okay, so the line integral is 2 pi. Okay, so what is the, okay, now let's compute that a different way. Okay, and the other way involves the curl of the vector field. So remember, the curl is like a cross product. So I put ijk, and I put my derivative x, y, and z. Okay, and then I'm going to put the component of the vector field minus y, the x component x, and this is not a vector field in 3 dimensions, it's in 2 dimensions, but you can still compute the curl. You just have to put 0 for the z component. Okay, and then you do the determinant of that. Okay, now you're going to get a lot of zeros. The only non-zero part is the k component, which is going to give you 1 plus 1, so you're going to get 2. So the curl is always a vector, it's 2k in this case. All right, and now we're going to compute the following integral. It's a double integral, so it's not lying when chapter 15 reviews pretty much everything we've seen. Okay, so I have to do I have to compute the following double integral. So I always three things, right? So what function do I integrate? I integrate the curl dot k. Okay, the curl is a vector. So I have a function, I have to do dot product with something, and that something is k. Now, what is the region of integration? It is the boundary, it's the region enclosed by the curve C, the unit circle. So in our case, okay, the region I integrate on is the one enclosed by this unit circle, so it's the unit disk. So that's my region of integration. Very good. Okay, now I plug everything in. So region D, that's a disk. Here I get 2k to curl dot k, so that's going to give me 2, and the x dy is just the x dy. So at the end of the day, this double integral is simply 2, the double integral over d dx dy. So since what I integrate here is a function 1, this reduces to the area of D in this case. And the area of D is the circle units, the unit disk, so it's just pi. Okay, so 2 times pi gives me 2 pi, and that's exactly the same thing as here, as the line integral. Okay, so what we did here is verify actually Green's theorem for that particular example. So here's Green's theorem. So if I have a vector field in the plane, so that's the plane version. I'm going to talk about the space version next week. So it's a vector field in a region R, and this region R has boundary, and the boundary is C. Then the integral of C, the line integral over C, is equal to the double integral of the curl of f dot k dx dy. Okay, so it's a very interesting theorem that relates a double integral, so the integral over a region, with a line integral, the integral along a curve. All right. There's another way to look at Green's theorem that doesn't involve the curl but involves the divergence. Okay. So what we do here really, right, when we do a line integral, we sum the component of f along the curve. So in some ways, if I go back to my picture, what we're doing here is summing, if you want, all these little projection of the vector field along the curve, okay? But another question, so it's all if you want the component of the vector fields that flows along the curve. But what about what flows outward, outside the curve, okay? And that's the other version of Green's theorem, and involves the divergence, okay? And here it is, so maybe I should actually put that in. That's the first version, and that's the second version, okay? So that's the curl version and the divergence version. Okay. So what is the divergence version? What I integrate is not the curl, is the divergence. Divergence is a number, right? It's not a vector, so it's just integrating the divergence, a function of xy, and I integrate that over the region R, that is enclosed by C. Now, on the other side, instead of integrating what is along the curve, right? So f dot the velocity vector, I'm going to do f dot the normal vector. So this guy, n, is the normal vector to the curve, and actually normal to the velocity vector. So you take y prime t and minus x prime t. If you do the dot product with the velocity vector x prime t, y prime t, this is going to give you 0. Okay, so that's the vector normal for the velocity vector. So what we're doing here, we are summing the components of F flowing out of the region. Okay? So let's check that version for the example we had. So that was our vector field. What's the divergence? Well, the divergence is derivative of each component with respect to their variable, and you sum them up. So the derivative of x of the x component, that's 0, and the derivative with respect to y of the y component, which is 0. So the divergence of f is 0 at every point. So therefore, when I integrate 0, I get 0. Okay? Good. Now, what's the normal vector? Well, this is the position along the curve, cosine theta, sine theta. The velocity vector is the derivative of that, it's minus sine theta, cosine theta. And the normal vector, right, as we have here, is y prime minus x prime. So y prime is cosine, so this is it, and minus x prime is this, so it's sine theta. So the normal vector is actually, in this case, and it's not always true, so we have to be careful, and the normal vector is the same as the position vector. Okay? All right, so now what I have to integrate is f dot n at the position theta, but if I do f, which is this vector, dot the normal vector, I get 0. So when I integrate theta from 0 to pi f, so this line integral, I get 0. So we have verified Green's theorem divergence version, since both the double integral and the line integral are equal. Okay? Good. Now, here's the proof of the second version using the first. Okay? So when I do the integral, I do the integral over the curve of the dot product, so of, let's say, the component f1, f2 for the component of f, dot product with this. So this is what I get. Okay? f1 y prime minus f2 x prime dt. But I can write this actually as the dot product of the vector minus f2 f1 with the velocity vector, right? Because this is the x component of the velocity vector, and this is the y component of the velocity vector. So what I have here is actually a line integral, which corresponds to the first version of Green's theorem, right? So it's integrating this vector field along the curve. But this vector field, it's similar to the one I started with, but you inverted the component, right? And you put a minus here. So let's call that G. So what you did was actually, so using the Green's theorem in green, ha ha ha. So this should be equal to the curl of G dot K. And if you compute the curl of G, so I do ijk, the derivative, now the x component is minus f2 and the y component is f1. So when you actually do the curl of G, what you get is del x f1 and del minus del y f2. So it's del x f1 plus del y f2. This is the divergence of the vector field f1, f2 you started with in the direction k. Okay? And so therefore, what you have, when you do dot k on both sides, you get that the divergence of f here in the integral. Okay? So it's just a little trick. All right. So these are the two versions of Green's theorem. And just let's finish with a picture. Okay, so this is some vector field. And so the curl version, so I have this curve C, right? So the curl version is actually, so let's put it in green, summing up all the components of this vector field along the curve, okay? Like this. Okay, so in this case, it goes like this. In this case, pretty much orthogonal. In this case, well, this case goes this way. So you're summing up, if you want, the dot product between the vector field and the velocity vector. So it's what is the part of the vector fields which is essentially parallel or collinear. Now, the divergence version is about what flows out. Okay, so you look at the normal vector to the curve, and you're actually summing up everything. So here I'm flowing in, and I'm flowing in. Here I'm pretty much parallel, so nothing is flowing in, flowing out. Whoops. This is flowing out. This is kind of flowing out. This is flowing in. This is kind of parallel, so I don't count anything. Okay. So why in the first version you're summing all the contribution of vector field along the curve, and it turns out that this is related to the double integral of the curl. And on the second version, you're summing everything that comes out of the curve, and that's equal to the double integral of the divergence. Okay, so that justifies a bit why I said at some point the divergence is about the infinitesimal flow out at a point, and the curl is about infinitesimal, if you want, rotational or whirl. Let's call it a whirl. Okay. So that's Green's theorem. Thank you for listening.